Last video, we introduced the balances, and we can do the balance on a single unit process. A single unit process is it's only one unit operation that has inputs and has outputs. Let's say that we have a unit operation where we have two inputs and one output. We can have more of them. And on a steady state, we state that the total balance is going to be that the inputs is going to be equal to the outputs. We have a steady state, we don't have chemical reaction, right? And then we can do it component by component. So let's say that this is mass 1, which has a composition of A and let's say of B. And then we have mass 2, composition of A, also composition of B. They will mix, and we will have mass 3, composition of A, composition of B. So the total balance is going to be mass 1 plus mass 2 equals mass 3. And then we can do it component by component. So component A times mass 1 plus component A times mass 2 equals the component A times mass 3, right? So this is going to be a balance by component. And this happens on single unit processes. But what happens if instead of having a single unit, we have multiple units? When we talk about a multiple unit process, we're talking about more than one unit operation, where we can have inputs and we can have an output, right? And then another unit operation, and then we can have its inputs and outputs. So it is important for us to state which is the system that we are going to be working with. And in order to understand the system, we need to understand what is a boundary. So the boundary is the limit of the system. So if we have these two unit operations, then we can say that we can delimit the boundary of our system as the whole process. This is one boundary. But then we can only limit our analysis to another boundary, which is the unit operation A, or we can state that we have another boundary, which is unit operation B. So when we're talking about the first boundary, which encloses all of the system, we can state one balance for the overall system. So once again, if we have here mass 1, and we have here mass 2, and then the one in the middle is mass 3, and here we have mass 4. For the overall system, we only are going to take what enters and what goes out from this system. So we don't really care about mass 3 here, which is in the middle. And the overall material balance will state that mass 1 plus mass 2 is going to be equal to mass 4. And of course, we have another entrance here that we need to take into account, which let's say is mass 5, right? So we have to take that into account. What enters is going to be what goes out. Once again, we don't have chemical reactions. Once again, this is a steady state. But then again, we can do the process for unit operation 1, which will state that the mass 1 plus mass 2 is going to be equal to mass 3. And we can do a balance for unit operation 2, where we can say that mass 3 plus mass 5 is going to be equal to mass 4. And these are total material balances. But of course, we can also do it component by component. So if we have, I don't know, here XA, XB, we have here XC and XD, right? I am stating that here we will have XA, XB, XC, XD. We have different components, we're mixing them. We can do it also, the overall for each component, we can do it per unit operation. component by component. So the amount of material balances that we can generate on a multiple unit process depends on the amount of processes that we have, but also it depends on the amount of components that we have per process. So we can have a lot of material balances in these processes which has more than one unit operation.